In this video, we're going to look at other properties of integrals and specifically ways to find even just rough and ready bounds for the value of an integral. If you're asked to sketch the function f of x equals 5 sine of 2 pi x, that's something we've seen before. But let's go through the steps just to be perfectly clear. This 5 here would be our amplitude. And the period would be based on the multiplier in here. The period is always 2 pi over, this is the natural period of the sine function. It's divided by this value here. And so we get a nice simple answer here that the period is equal to 1. All right, so if we sketch the sine graph and it has period 1, then what we can do is sketch it going up and coming down and going back up again. Then we can take a look at the question here. Can we use an area argument to prove the statement that when we integrate this function, so this is the graph we have sketched, that's our integrand, and then we're going to integrate that, notice the interval from 0 to 1/2. Well, we're talking then about this region here. That is the exact value of the integral from 0 to 1/2 of 5 sine of 2 pi x dx. Well, can we say it's larger than 0? Absolutely. If the graph is above the axis, then we are definitely going to get a positive quantity for this integral. A way to think about that, though, is to look at the lowest height. Think of the whole trajectory here. The lowest height on this graph is a 0. So we could build a little rectangle with height 0 and width 1/2, and that's where we could get this 0 as a bottom possible value for the area from. That's a nice inspiration for where this mysterious 5/2 comes from. Well, if we go to the peak of this graph, the amplitude is 5, so this peak is at 5, and what we could do is recognize that whatever's happening to the function, it's 5 or less. And guess what the area of a rectangle that is 5 high and 1/2 wide is? Well, that area is 5/2, height times width. And so that gives us the 5/2 on this end. So what we can do is look at the range of values of the function itself and multiply it by the width to get these kinds of bounds. If we want to formalize this a little bit, what we can do is imagine a function. We can imagine an interval that we're considering, and then we can identify the smallest point of the function. So we say this graph is doing what it's doing. The smallest value of the function, we'll call it little m, is there, and it also will have a largest value, big M. And what we can do is bracket the area underneath the graph, the integral, with one of two rectangles. We can bracket on the bottom end by saying, well, the area under the graph of f of x is certainly going to be smaller than taking the smallest value of f and making a rectangle out of it. That would be m times b minus a as an expression. Width times height. And so that's how we get that formula there. We'll change the color here. We can also say the area underneath the blue line, that's the integral of f of x, this region here, that will be smaller than what I would get if I took the highest possible value of the function and built a rectangle. So that big area there is capital M times the width b minus a. And so we're again tying back rectangles, a simple approximating shape, to something more complicated, the integral value. It is worth noting that these maximum and minimum values that we get are quite crude. They're just ballpark things. They're values we can get easily and quickly, but they are not very accurate necessarily. There's the occasional moment where we can get something much more precise without, again, any serious calculus calculations. Let's take that same graph where we had our sine function with period 1 and amplitude 5. And ask yourself now on the interval from 0 to 1 what the integral would be for that. Take a look at the options here for a moment, and then we'll check in. All right, so for this, Very similar to some earlier examples with odd functions, though we're not really using that here. We're using the symmetry of the sine function to recognize that this area would contribute a positive amount to the integral because we're adding positive function values. Whereas this area here, let's do it in a different color, would contribute negative totals to the integral value. But because we know the sine function has the same shape above and below the axis here, repeats itself, those are going to be equal and opposite contributions to the integral. And so we're going to get an integral value of 0 by the time we're done. We're going to get perfect cancellation of the positive and negative contributions. So sometimes we'll get lucky with cancellations like that, and that can sometimes help simplify a more complicated problem. It's also useful in many cases to be able to compare the size of two different integrals. So far we've compared values to integrals, now we're going to compare two integrals to each other. We'll do that or inspire that by looking at a scenario where we have two cars moving, starting at the same time and from the same starting point. The first car is going to move at velocity v1, which is given by the formula t, and the second car is going to move at a separate, different velocity, which will be t squared. And we're interested in the first second of travel. So we indicate time 1 in seconds here, and our velocity in meters per second here. Then v1 is a straight line, like so. The second velocity is given by the formula t squared, and we just have to be careful here that the parabola actually starts flat and then goes higher afterwards. And so on this interval from 0 to 1, the second car, the parabola, is actually moving slower than the first car. After 1 second, the parabola wins, we're going faster in car 2. But on this interval 0 to 1, the green line is always below or just touching the blue line. Understanding how they are moving relative to one another, we can ask which car travels further in the first second. Well, the first car, its travel distance is exactly the area under this graph. That area is equal to the net change of position. And if we compare that to the parabola, like so, that's distance traveled for car 1. This area here is the distance traveled for car 2, and it's going to be smaller. How would we write that? We would write the integral from 0 to 1 of v1 of t dt. Quick side note, checking units. This would be meters per second times seconds. That equals distance traveled, is going to be larger than the integral from 0 to 1 of v2 of t dt. But why is that true? Well, it's true because the velocity of car 1 was always higher than the velocity of car 2. So if you have this relationship where one velocity is higher than the other, then no surprise, the integral or the area underneath the graph of this is going to be larger than the area underneath the second graph. And that's just formalized here in the opposite order. If we have one function that's always smaller than another, then the area underneath the first is going to be always smaller than the area under the second. If we want to be strict, we could have them less than or equal to and less than or equal to. And again, that's a nice way we can bracket maybe a complicated function with a simple function that's larger, and then get a comparison of the areas or the integral values.